Hi all, this is Claudio from expertfea.com, recording for you the 6th webinar meant to help improve your finite element analysis skills, especially in ANSYS Workbench. Also, because I was asked many times in the past what computer-aided design tool I use, my answer and my advice for you is to use ANSYS Spaceclaim, because it deals very well with the non-native files with step, IGS and parasolid files which come from a different CAD software. First, little history. Why I think Spaceclaim is awesome for FEA engineers. Autodesk, which has the Inventor package, also many others, acquired a few years ago the FEA package named Algor or Design Check. Also a few years ago SolidWorks has built into his package the FEA software named Cosmos. Dassault Systems, which is the well-known CATIA producer, also acquired the FEA software named Abacus or Simulia, and PTC, which has a ProEngineer, also built into its CAD software ProMechanica. What we see here is that top computer-aided design companies acquired the finite element analysis software. Only ANSYS did the opposite. ANSYS is the only FEA company that bought a CAD software. A software that is very easy to use by stress analysts, by FEA engineers. So, what we will do today, of course, after we solve this crash, we have searched on GrabCAD for a hexapod mechanism, and we will work on these two files that we downloaded. This is one file that we downloaded, hexapod robot. And this is the second file, Stuart Gao platform or something like this. So let's drag and drop these files. This is the first file and this is the second file. Originally they are step files, so they are not native to Spaceclaim. Looking a little on the first file, let's say for the purpose of today's work, we're going to choose which one of the 3D models is most suitable for our lesson. To better see what happens inside these parts, let's make a section. We will triple click an object, hide it, and we did this just to isolate an axis, and we press the plane button. We have here the section mode button, and the section is done. In order to view, let's say, from the normal direction, to establish a plane view, we click this button. What we observe is that this is not extremely well made because we have an interference in the spherical joint. These two parts are not, let's say, logically joint or welded. Also on the other side there is an interference and there is no allowance or gap between the parts. So let's show all the parts. We click the plane and go again into the section mode. You see what happens? This rod enters this tube. Only the end of the rod with the spherical joint, let's say, is not logically welded to this part. Also what we have here is a lot of chamfers. Let's delete the plane. We have some fillets. Sincerely, this kind of looks like a lazy work. Let's go to the other assembly. This is the second assembly. We'd like to look directly inside to see what happens in the section, let's say. So we will triple click a part, we hid it, we select the axis, we click the plane. Now a plane is created. We right click, show all the bodies, and now we just press the section mode. This is how one of the members look. So here we have like a thread. The spheres interact very well, except this interference. The tube is very well made. Also here it's a threaded connection, let's say, and the diameter of the spheres they are equal. Sincerely, I like very much this model, and this is the model we will use for today's FEA example. What it needs though, in order to simplify our model, we will join these parts. Alright? We will delete the holes. We'll then join the end of the members of the tubes. So let's do this. We will triple click each member. 1, 2, 3. We'll hide the other bodies and look inside. There is this hole. It's pretty complex, let's say. We right click it and choose select depression. So the first part of the hole, we just deleted it, and we can, with the when you don't like a command, you can hit escape. We have this hole, just click both faces and the delete button. This was all. So right click, show all bodies. Let's see in section what happens now. So you see here the hatches interfere. This means that the rod now is full, there is no hole. Regarding this part, let's just suppress, delete this boss, this dome. We exit the section, triple click the part, hide others. We can select this surface. We press the U button, which means until this surface. This means we extruded it to up to this surface. It's like the result from a cut operation. So Right click, show all. We select the plane, we go to the section mode and look inside. Look, it's very nice. What happens here, because this end, let's say, of the rod was repeated or copied with a pattern, this means that the modification we have done here applied to all the similar parts. We just need to delete this hole from here. Triple click, hide others. We have this hole. Select the surface, delete. Right click, show all, select the plane again, section mode, section. So everything looks extraordinary now. What I will do is, why not? I will join. I will merge the end with this part. Let's see what happens. So we go to the combine button. We select the tube, the rod, let's say, and then we click this button, which is called select bodies to merge, and we need to join it as seen. So what you see here is that all the parts merged because they are patterned, they are copied, and this means that these other parts need to be deleted. We exit the command with escape, and we can just triple click and hit the delete button. So now we have this very nice model, which is very simplified for our FEA. Unfortunately, we lost the end of the rod. Let's hit undo. And see if we can find a solution. Yes. Let's go here and apply the same command. So to this part, we will attach with the combine command this end. Let's see what happens. Escape. 1, 2, 3. And now we didn't lose anything. We have everything we need. Let's go into the section and see. You see, everything is merged. This means the fact that we don't have redundant contacts and constraints, because literally we have only two parts here. Moreover, what I would like to do is join these sockets into these frames, which is very easy to do. We press the combine button. This is the target, and we would like to choose, select bodies to merge, and we choose each socket, let's say. You see that it gains the same color. Super. We hit escape and we do the same here. Combine, yes, bodies to merge, and we select the sockets. Escape. Let's see in section what have we done. Look, we have a bottom part which contains the socket. We have this outer cylinder, let's say. We have this inner rod and the top frame, let's say, which is very simple and easy to use from the FEA point of view. Let's here just create some radiuses. We go to the pull button while we are in the section mode, yes? We go to the pull button, we click this vertex and just push to create a round. Let's enter with the hand 1 millimeter, and this is all. So the radius was done. And let's check if we can do the same to the other parts. So what we will need to do is hide these rods in order to see the edges that we need to fillet. So with Control pressed, let's click more edges. Yes. We push a little on the arrow and just enter from the keyboard 1 millimeter. And all the radiuses are done. Let's do the same with the bottom sockets, let's say. We triple click each body. Right click, hide, and we do the same. With Control pressed, we choose all the edges and we pull as we did before. A little, and we enter 1 from the keyboard. Right click anywhere, show all. Look, if we go into another section plane, let's say, select an axis, we create a plane, we go into the section mode, right click, show all, plane view. Look, everything is awesome now, no interference, and it looks ready for the FEA. So we can delete this plane. We will close the first assembly, which required a lot of work and corrections. And let's name it was good here. 2015 July 15 hexapod webinar 6, and of course our preferred extension Parasolid. What we will need more to do, because this top platform, we will, let's say, we will apply an angle, we will rotate it. Let's just create a hole through it. You'll see that it will come very handy in the future. So this is a plane into the which is very useful to create the hole I mentioned. Let's go to the sketch mode. We press again the plane view, and we're going to create a hole here. We can be very generous. We can enter from the keyboard, let's say 10 millimeter. We return to 3D mode. Yes. We select this surface. What we need is to cut. We press the cut, and we press also this pull both sides, and we just pull from one of the arrows. Look, the hole is created. This pair of holes will be very useful when we will apply a coordinate system, and we will choose an axis to create the angle or the rotation of this top platform. So let's delete this plane and save again the part as a parasolid. Double click, replace, yes. Let us close Spaceclaim. For a few seconds in this break, we will remind you to visit our website expertfea.com, which is updated very often. As seen on the blog page, we have lots of tutorials, solved FEA files, which is very unique in the world. And these are our latest books. The free webinars we present to you. Also lots of discounts, our partners page, and how to contact us. Moreover, if you'd like to understand how an FEA engineer works, how he thinks, how she approaches the FEA, just go to grabfea.com, visit our webpage with our example. Then take your time and go to our friends, our collaborators, who also have lots and lots of FEA, very unique and pretty genial, some of them. Not only structural, but also thermal and with fluid dynamics. We are very sure that you will find lots of inspiration on this grabfea.com website. So we can now close this. Let's go to ANSYS. We can approach transient structural FEA. But because we don't need, let's say, the inertia or the speed or acceleration, let's select the static structural module. We'll copy and paste the name of the file in order to rename or to name our project. So let us rename the geometry. We right click, import it. We double click the model. So let's rename these parts, or at least what is possible. This we will rename it as bottom plate. This would be the top plate, and we have cylinder are the, let's say, the inner rods, and the tube are the outer tubes. Alright, so ANSYS discovered some of the contacts. It put them as bonded, but we will not need them. Let's right click, suppress, and now let's create the joints that exist into this assembly. So while being on the connections toolbar, we go to, let's fix the bottom plate, body and ground fixed. Also, we will apply a rotation on this top plate, as I have mentioned before. Body and ground, revolute, and we select a hole. You see the rotation axis is Z, and this top plate will oscillate about this Z axis. So, more joints. We have 4 spherical joints here. Let's start from here, let's say, from the green one. Body and body, spherical, even though we do not see it, it is selected. The inner spherical face of the bottom plate. You see here in the naming it says that we have the bottom plate which is joined to the tube. Yes, this is the bottom plate and this is the tube. In order to see them easier and correctly, we can press the body views button and you will see them here. This is joined with this, which is very nice. So we're on the green rod. Let's go to the next one. Body, body, spherical, we see that is correctly assigned here, and we repeat. Spherical, alright, this is a pretty repetitive process. We can verify what I do here in these windows. Body and body, spherical, let's click a little the geometry. Yes, we have one more joint. why did I suppress the contacts? Because sincerely we're not interested in what happens here in this, let's say, interference. So we have created the joints for the bottom plate. Let's verify a little what we have done. This is separate. Alright, let's now do the same thing for the top plate. It's pretty boring, but it needs to be done. Body and body, spherical, again from the green rod. Body and body, spherical, again, and this is the last. So these are the top joints. Let's see them. Super. Everything is in order now. Do we need what happens into the bottom and top plate? No, we don't need. So let's just select them and choose their stiffness behavior as rigid. This will help shorten our solving time. Right click, generate mesh. Oops. This is pretty interesting. Let's increase the relevance. Now it looks nicer. Let's go more with 90 here. So, can we obtain a section plane? Let's try and do this. As for the purpose of this tutorial, this mesh works. Feel free, because you have the 3D model on our website, feel free to increase the relevance, to increase the mesh size. Just use your imagination. Regarding the loads, let's create 2 steps. In 2 seconds, large deflection on, and define a load joint load. And this joint load will just rotate this plate. Yes, we'll rotate it. We cannot rotate it very far. Let's say we'll rotate it for 10 degrees on this side, on the positive side, and back let's say 30 degrees. Let's see what happens. Rotation, and on degrees we have here 10 degrees, and here I said 30 degrees. Means minus 20. So the interval between 10 and minus 20 is 30 degrees. Let's save our project and solve this FEA. Before doing this, what I have forgot is to define translational joint into the pistons, and that's what we will do now. Body and body, translational, this is the reference, this, I'm sorry, yes, and this is the mobile. Body and body, translational, reference, mobile, body and body, translational, body and body, translational, and this is the last. Alright, body and body, translational. So now we have the pistons. Everything should work awesome. Save again, right click, solve. Yes, why not? Let's clean the mesh. Do it again and solve. It should go very fast. We choose force convergence here. It tries to converge. It's just a matter of time until force convergence will intersect the force criterion curve. And it happened. So I will pause the video for the interval that the FEA is solving. And come back to you then. So, unfortunately, the FEA did not converge, so it stopped at the second 0.3. Let's try and see what are the causes. Let's look a little on the solver output. So what have we here? Two error messages which say solution not converged. Does not say very much. 18 joint elements with Lagrangian multiplier option do not satisfy joint constraint conditions. Reference force value times the tolerance is used by the Newton-Raphson method for checking convergence. The calculated reference force convergence value is less than a threshold. This threshold defaults to 1 at the power minus 2 or is specified as minimum reference on the CNVTOL convergence tolerance command. Check results carefully. So it's a problem of the convergence. Let's try here and be more generous with the mesh. If now we have around 19 nodes with 100 relevance, what will happen? This is the same. Let's apply a sizing. An element of 5 should be nice. Also, let's do the same with the plates, because it is important what happens in the here in the sphere shape. I'll show it a little later. So now the mesh looks awesome. All the values are very high. Instead of 5, 7, 57. This is nice. Let's just hide one of the parts. There is no mesh made here because there is no contact here. Alright, let's solve now and see what happens after we save it. Right click, solve. I will pause again the solving and resume later. Let's check the force convergence. It also doesn't look very well from the beginning because we have a large difference between the maximum and the minimum of the force convergence and criterion. But we will see what happens. After a few minutes of solving, I decided that I do not like the trend of solving. So let's stop it. I will increase the mesh size in order to obtain fewer nodes, let's say 8 mm. and finally 9. $30,000 looks very nice. Yes. So what I suggest is here to change the auto time stepping to on. The initial time step will put 0.1, 0.05, and here 0.2. Again, save. And before hitting the solve, let's define some deformation and stress. Let's look a little on what happens in a forced convergence plot. Here, now there is not such a big difference between the forced convergence value and the forced criterion. And we achieved the convergence from the beginning. So what we need to remember is that we either, let's say, adjust from the mesh size, or either adjust from the time step. We have a bisection now. And I will return a little later with more news. What we can see now is that the FEA converges nicely, and we will wait until here is written 2, meaning the end of the solving. So I will be back in a few minutes. So now we're near second one, and the FEA converges very well. I'll be back. So I spoke too soon because the FEA stopped. It didn't converge completely. Let's see what happens. It behaves very nice. Let's draw a section plane here. the stress is negligible because literally we don't have any contacts in the spherical joints. So what remains for us to do? Let's save the project. We will clear the generated data. We revert back to program control, time stepping. And because we're pretty desperate, we'll change the behavior of the joints from rigid to deformable. Of course, only the reference is deformable. And here vice versa. Let's just hope that it works. Right click, solve. So it converges. Let's see until when. So it seems like it was a very good idea. We will not stop the recording because it seems like everything is fine now. Regarding the lack of stress, you remember the small values of stress, almost zero. It's because we do not have a gravity defined. So let's say the outer tubes do not rest on the inner rods, so there is no touching because of translational joints. And literally, apart from the fact that the top plate pulls and pushes these inner rods, literally there is no load, let's say, on the parts. This is why stress does not occur. If we will activate the contacts and change them from bonded to frictionless or frictional, and suppress some of the joints. Then we will have let's say a resistance between the parts, also between the plate and the rods and the tubes, and then stress will appear and we'll have higher values. As I said, apart from the fact that you can play with the element sizing for your own practice, you can also change the rotation, keeping in mind that the top plate should not, let's say, touch the outer tubes, so there should be no contact between these sockets and the outer tubes. What is needed for an FEA engineer is to be extremely creative. And FEA is pretty complex, because every time we deal with material problems, with geometry problems, with mesh, variables, with analysis settings or solver, let's say, the restraints, loads, and somewhere here contacts. So the FEA engineer should deal with all these variables in a timely manner. He should balance the material, the geometry, the contacts, the mesh, the time steps, the restraints, the loads, all these in the same time in order to achieve very fast response that is also realistic and can be validated in practice and then with experiments. This is what makes this domain, finite element analysis, very challenging, very difficult, but also very easy, challenging, and desirable for the engineer who is passionate about this field. So the FEA finished. Let's look a little on the deformation. Initially this is how they look, but when we animate them, they should look better. Here, you see, this is the proper behavior that would we would like to see in such an assembly. Also the stress, which is very negligible, because literally no load is exerted on these parts. If we're keen to see some angles made described by the parts, we can go to the so these are the joints and the connections in the assembly. You press the solution information and unpress the worksheet button. Yes, you can see the fixed bottom plate. The spherical joints and translational joints. So what I was saying is that we can access by selecting solution, we can access an extra set of solution items, and we can select everything that deals with angle. Let's see if anything is suitable for us. I didn't select this because this deals with the composite plies or layups. So right click, create user defined results, right click, evaluate all results. Let's see which of them is makes sense, is suitable. So this looks very nice. And if we look on the global coordinate system, we can somehow distinguish some angles related to the axis on which we look. So between 5 and 10 and minus 24 degrees. This is pretty symmetrical. These values are interesting. Angles shown with the help of small coordinate systems. Coordinate system in each node. You see node, mid node, 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 mid node, node. And I leave to you to look more and investigate everything that is related to this. What you can do more is select these two parts and assign their stiffness behavior as flexible. And also you can try and here inside you can apply a spring. This meaning that you'll have load, resistance and stress between these in these parts, yes, because of the resistance created by the eventual internal springs that you will assign here. So hoping that this session was useful because it contained the Spaceclaim modeling elements and ANSYS Workbench mechanism applications. I wish you all the best and good luck in your career and life. Goodbye.